Okay. These are 32nd lecture and today is 11th. Yeah. When I was naming the file, I did that correctly. I forgot to update that also here. So before I start to lecture, I want to emphasize the fact that I'm here for you all. I'm your advocate, and I take your suggestions seriously and use your suggestions on anything that you tell me. So based on the discussions that we had previously in the class, I updated all the study guides and course materials from last semester sooner on Canvas, so you have like more questions to work on before doing your homework if you need like more questions. And also the previous 2 lectures, I had like some questions that I couldn't solve in the class, so I also included the answers to those on Canvas under the lecture of that date. So you have more questions there, and so basically you have like some sample questions that you can work on, okay? And I always encourage any suggestions, and as long as we communicate well and have a mutual understanding, I believe that all of us can succeed in our aim. My aim is for you all get a good grade, and your aim is similar to mine. Just individually, you get good grades. And any questions about makeup exam, quizzes? So I posted your next quiz, basically quiz 4 and homework 12 on Canvas. The deadline for homework 12 is this Wednesday. This deadline is this Friday, okay? And as I said, if you want to take makeup quiz 3, just email me so I open that for you on Canvas. And if you want to take the exam or like the makeup, exam 2 would be this Friday, as I mentioned. Friday, 3 to 4, 4 to 5, 5 to 6. And if none of these work, just email me. I try my best to accommodate your schedule. And also, I'm going to have office hours this evening. Office hours. And I think I assigned 3 to 5. But, you know, I try to be at my office later on too. And also tomorrow is a little tough for me because we have like things going on in chemistry department. But on Wednesday, again, I try to be at my office like 3 to, I don't know, 6, 7, you know. So I highly encourage you to email me so I make sure that I'm at my office, because sometimes I get hungry, I want to go get food. So I make sure that I get food not the time that you're going to show up at my office, okay? And the same thing with Thursday. I try to be at my office like 10 a.m. to, like, I don't know, 1 p.m. And also in the afternoon. So I have like some meetings going on in between too, but 4 to 7, right? But I highly encourage you, again, to email me so I make sure that I will be at my office. So if none of these times work for you, again, email me and I work out with your schedule, okay? I just want to make sure that all of you know the course material and have the opportunity to talk with me. And then I have the opportunity to explain the materials to you, okay? Any questions? No questions. Put this here. So don't have to deal with that. So last session, we talked about light, which is form of electromagnetic radiation, right? And I told you that if I have a prism and I have like a light source here, visible light basically, right? Or like white light, we call that visible light or white light. And I pass that through a prism, I can see these rainbow colors, right? And can anyone tell me what does each color correspond to? So I have different colors. So what does that mean that I have different colors?
The colors correspond with the wavelength and the frequency, doesn't it?
Exactly.
So red is less, while violet is more.
Yes. So basically, so red is less what? Less energy, right? Or less, or like a smaller frequency. But it has longer wavelength. Comparing these colors with one another, okay? So remember, energy and frequency, they have the same trend. If you have some wave that it has low energy, it is also small or low frequency. But wavelength and frequency, they are opposite, and also wavelength and energy. If you have longer wavelength, and always remember this example, you see that this wavelength is really long, so the frequency is a small, or energy is a small, okay? But if you have like this, for instance, frequency is, higher, and the wavelength is smaller, okay? And this is some sort of question that I always ask in the exam. Which of the following colors has lowest energy? And I give you like, I don't know, yellow, green, blue, indigo. So as long as you know this spectrum, it should be fairly easy. And that is specific to white light, okay? And last session started, and we also talked about electromagnetic radiation and also the whole spectrum, remember? Any questions about this? Good. So we were saying that we talked about white light, but even if you have like certain elements, for instance, neon, and we give neon electric energy, we see neon generates light. And I asked you, do you guys ever see neon lights? Right? So what happens is that we give neon electric energy, and neon releases that energy back in the form of light. So that's why we can have also elements that we heat them, and also they generate light by themselves. And we also, I included these pictures from your book, that we can have mercury lamp, which is on the left here, mercury lamp, which appears blue, and we have hydrogen lamp here that appears pink. So depending on what element we have, if I tell you, in advance, I give you information that if I have pink color, that corresponds to hydrogen, and if I have blue, that corresponds to mercury, right? If I give you this prior information, and then I give you some other, not in these pictures specifically, but I have here some unknown element, I give you that, and I tell you that I saw blue color. So what element do I have here? If I give you this prior information, you know that that corresponds to mercury based on the light that I see. It's kind of similar to what we were telling previously in the previous slide. Depending on what wavelength we have in white light, we have different color, right? And you also have numbers associated with each of the wavelengths that correspond to different color, but I expect you to know those numbers, But as long as you know different numbers correspond to different wavelengths correspond to different colors, okay? So this is what most of you are going to see in your lab tomorrow. Based on different colors and different wavelengths we have, we can distinguish what elements we have. So this is something that scientists use to identify different elements. And I'm going to talk more about that, and that is the purpose and subject of our session today. But you may ask me, so why do we see colors, right? So what happens in the subatomic scale that we see colors? What happens? Is there, yes?
Electrons are losing and gaining energy, and when they jump from different orbits, they emit light.
Exactly. So what your friend said is what I'm going to just talk about now in the next slide. So we briefly talked about Bohr model, and this is actually how Bohr came up with this model, with this atomic theory that I'm just going to talk about. So if we have white light, and this is something that I always ask in the exam, if I have white light and then pass it through the prism, just what I told you in the previous slide, I showed you in the previous slide, we see this spectrum here, which is like a rainbow, and that is continuous. What that means is that if you just like here, I tell you exactly what color I have. You can say like, that is orange. Took me a while to think of the English name. This is orange, but we don't know exactly. It's not like separate line, or like here, the red, we have like different shades of red, right? It's kind of like your paint software that based on the numbers that you put, you get like different type of red. But it's not, distinct. So what I mean is that for white light, you don't get one line for red, one line for blue, one for green, one for yellow. Let's see if I can also generate orange. So, okay, that didn't work out. So you get the idea, right? So, orange, okay, for some reason it wasn't selecting that. And also indigo, right? And then purple, probably spending so much time trying to, okay, done. Okay, if you accept that color, purple. 1, 2, 3, 4, 5, 6, 7. Okay, so it's not like we just see, that is not the spectrum of the white light after it passes through prism, okay? That is continuous, and you see a spectrum. Does that make sense? But when you have elements, for instance, here you have like hydrogen light spectrum. We do the same experiment, but here instead of having white light, we have hydrogen lamp. And then we give hydrogen energy, and then hydrogen releases that energy, and then we record this, in a photographic film, we kind of record this picture that we see here. And we call that emission spectrum. The spectrum that is generated based on the emission of hydrogen atoms. So we give hydrogen some energy, they receive it, they store it, and then because they are unstable, that I'm going to talk about momentarily, they give back the energy. When they give back, as your friend said, electrons, when they release back the energy, we see this spectrum here. But for hydrogen, that is not a spectrum anymore. Can anyone tell me why we don't have a spectrum when it comes to elements? For instance, hydrogen. And that is how Bohr came up with the atomic theory that he had. So as we said previously, we talked about Thomson and also Rutherford atomic theories, right? And the most updated one that we learned was Rutherford, that he said we had like nucleus that has positive charge and we have like electrons around it, okay? And he didn't specify where they are. But based on this observation, Bohr realized that there are certain amount of energy. So each of these lines that we see here, and as you saw before I kind of like messed that up, each of them, they have different colors. Can you see? Kind of like harder to see here, but this one is kind of like, you have like these lines that you have, and I don't ask you which color is what. The point is that you have different lines, distinct lines, each of them different colors. It means that these correspond to different amount of energy. Does that make sense so far? Any questions? So how Bohr explained this fact is the following. So he said, this shows us that the energy is quantized. And that means what I'm telling you here. If we have nucleus here, right, and maybe it's just like more feasible that they have like generate the picture here. And nucleus has, as you remember from like chapter 3, we have protons and neutrons in nucleus. Neutrons are neutral, they don't have any charge, but protons, they have positive charge. So in general, nucleus has positive charge. And then electrons are around this nucleus in different orbits. What it means is that, we can have one orbit around this nucleus, and we call that n equals 1. So we denote different orbits or different shells around nucleus by the number n. Okay, so we have shell, which is the same as orbit around our nucleus. Okay, and that can have maximum 2 electrons in it, and we denote each electron by a dot. Okay, and if we have n equals 2, which I try to have like a good circle here, that can have maximum 8 electrons in it. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And can anyone tell me how would I know? So these are the maximum number of electrons that can be in the first orbit or second orbit. But how can I know how many electrons I have in a specific atom? For instance, if I tell you how many electrons I have in hydrogen, what would you tell me? 1, exactly. You look at your periodic table, read the number on top, which is your atomic number. So atomic number is the number of protons, which is in this case 1. And since our atom is neutral, number of electrons and number of neutrons are the same. So number of electrons is always also 1. And in case of hydrogen, we don't have any neutron. That's why the atomic number and mass number is the same. Both of them are 1, okay? So in the case of hydrogen, number of neutrons is 0. So if I tell you to draw the structure of hydrogen, one hydrogen atom, based on the Bohr model, what you do is that you say, okay, I have my nucleus, which has positive charge. And in this case, we only have 1 proton, right? And then you say that, okay, in n equal 1, and I'm trying my best to have a good circle around this. Okay, so in n equal 1, how many electrons should I put? 1, right? Because I have 1 proton, 1 neutron. So I put 1 electron here that has negative charge. So I'm going to erase these ones so I have space here for what I want to demonstrate. So these different orbits, although I don't have electrons in them, but they still exist, based on Bohr model. So we also have n equal 2 and n equal 3. But we don't have any electrons in them, right? So what happens when we give hydrogen in that lamp energy, when we warm it up, is what happens is that this electron that was here in n equals 1, it travels, for instance, in n equal 2. Now this electron is here. Okay. Or if we give it more energy, it can also travel, for instance, from n equal basically, if I have like the same one, it's also possible that this electron goes to n equal 3, right? Depending on how much energy I give them. But this electron cannot come here, right? It cannot be between the orbits. That's why we say the amount of energy is quantized. And what that means is that we have like certain amount of energy between here to here or here to here. These energy levels are quantized, meaning that there are like certain amount that this, so if this electron travels from here to here, that associates, to this much of energy difference. It cannot be any random number. It's whether n equal 1 to n equal 2, or n equal 1 to n equal 3, or n equal 2 to n equal 3, and so on and so forth. But this electron cannot travel from here, right? For instance, to here, as I said, or like here or here. These won't occur. Okay. But this electron, if I give it enough energy, can come from here, n equal 1, to n equal 3. Okay. And as your friend mentioned briefly, when I give this electron enough energy to come here, now it has more energy, right? I warm it up, and then it goes to a higher level energy. So what happens is that this electron now is unstable. And usually in nature, always, atoms, molecules, electrons, everything wants to have lowest amount of energy possible. And that is how we write, or scientists come up with new compounds, or this is how in nature atoms bond together. So the reason that we have, H2O as water, not like the other configurations, or like not the other combinations, is that corresponds to the lowest amount of energy possible for that specific compound. Does that make sense? So what I'm trying to convey to you and convince you is that this electron here, I try to show it with another color, this is unstable. So it wants to go back to lower energy level. So what happens is that when it travels back to n equal 2 or to n equal 1, it releases heat. It releases some amount of energy. And depending on this energy amount, that energy amount corresponds to different wavelength. And depending on that wavelength, we see different colors. But we see single lines, distinct lines, because the amount of energy is quantized. So that's why in hydrogen, you see, we see different lines, distinct lines with different colors, right? So that is the reason. And this is how Niels Bohr came up with this atomic theory. So he observed this model here, he observed this in his laboratory, and then he thought to himself, if electrons were just randomly around nucleus, as what Rutherford said, we should have seen a continuous spectrum, right? It could be any possibility, so electrons were everywhere. Since he saw certain lines, he realized that this model is not correct, and the energy is quantized, meaning that each energy level, n equal 1, n equal 2, n equal 3, and so on and so forth, they have certain amount of energy. And depending on where electrons land when they're losing energy, we see different colors. Does that make sense? So this is what you're going to use in your lab tomorrow and this week, basically, that based on, if you know the emission spectrum for different elements, right? And then when you have some unknown compound that you are given, based on the library that you have of different emission spectra, you can distinguish what element you have. And this is the whole thing behind the spectroscopy. that based on, we have like a library of things that we know, and based on that, we can discover the unknown compound, or recognize it rather, what we have. Any questions so far? Everything I said makes sense? Does it? Okay. And we have also some expressions here that I'm going to write here that we see in emission spectrum. Does that make sense? And depending on how many electrons we have, for instance, hydrogen, it only has one electron, so the possibilities would be like 4 different possibilities. So, and you don't need to know specific, and I'm just like making up an example to demonstrate the point. For instance, from n equal 4 goes back to n equal 3, or n equal 4 goes back to n equal 2, And somehow, and the thing that is important to know here is that if I ask you, here I have the nucleus, right? And then I have here n equal 1, here I have n equal 2, and here I have n equal 3, okay? And I tell you, I excited the electron and it went like to n equal 2, n equal 3. And then I tell you this electron from n equal 3 goes back to n equal 1, and also this electron from n equal 2 goes back to n equal 1, right? And then based on what I just told you, I see different lines corresponding to that 2 different emissions, right? One of them is n equal 3 to n equal 1. The other is n equal 2 to n equal 1. Are you following what I'm asking? Or what I'm saying rather right now? I'm saying we have like, one electron, or like it can also be 2 different electrons. But we have like 2 different emission spectra. One of them is n equal 3 to n equal 1, the other is n equal 2 to n equal 1. And I told you we see 2 different lines based on these 2 emissions. And I asked you which of these has higher energy. How do you answer that? Exactly. So what your friend did, in his head, he calculated, he was like, okay, here, if I go from n equal 3 to n equal 1, I told you each of these orbits, they have energy associated with them, right? So we have like this energy difference, and also n equal 2 to n equal 1. So which one has the higher energy difference? Does that make sense what I'm asking? So here, is this higher or this? This one, the first one, right? And if it's kind of like difficult to compare, you can also give examples to yourself. Say that, for instance, n equal 1, if it corresponds to 1, right? Or like this one corresponds to 2, and then this corresponds to 3. And I'm just like making up numbers. These are not correct. But just for the sake of comparison, I say that, okay, 3 minus 1 would be 2. 2 minus 1 would be 1. So this number is higher. Does that make sense? So these correspond to higher energy. So for instance, if I give you something like this, and I tell you I see 2 colors, okay? One of them is, in this emission spectra, one of them is red, one of them is blue. So which of these 2, this or that, which of these emissions would be blue? 3 to 1, right? Because that has higher energy, and between these 2, we know blue has higher energy. Does that make sense? I can also ask you which of these have higher or longer wavelength. In order to have longer wavelength, we should have lower energy. So which one would be red or blue? Which one would have longer wavelength? Red. Are we comfortable with answering these types of questions? Good. Okay. So this is basically what we mean with this. And I asked you in the last class that is the following statement true or false? That when we have the emission spectrum of hydrogen, that emission spectrum is continuous.
False.
That is false because we just see distinct lines. Okay. And the other thing that is interesting to notice is that when you have only one electron in hydrogen, you have 4 different lines. So there are different possibilities. This electron, it has been excited and then goes back from, for instance, n equal 3 to n equal 2, n equal 3 to n equal 1, n equal 2 to n equal 1. And I'm just making up these orbits, But you have 4 different possibilities. And then for neon, you have several. I cannot even count this, right? With just like this graph, because there are like so many of them. And how many electrons neon has? Just looking at the periodic table, neon is group 8A. Can anyone tell me how many electrons? Can you see that? It's 10. So now that we have 10 electrons, there are like much more possibilities. So I give you these and hydrogen and then tell you which element has more electrons. Yes?
Well, isn't the combinations possible more dependent on the number of shells there are than number of electrons?
So number of shells so the question that was asked was that the number of lines, does it depend on number of shells or number of electrons? So it depends on number of shells, but shells and orbits, they exist even for hydrogen. We have n equal 1, n equal 2, n equal 3, all of those exist. But for different elements, this is number of electrons that differs. Does that make sense? And depending on how many electrons we have, more of them will be excited, and now they want to come back to lower energy states. So you have like different number of electrons, different possibilities. So you see different numbers of lines or like different colors, different wavelengths, different emissions. But it depends on the number of orbits as well, because for hydrogen, probably not so many electrons goes to like n equal 10, for instance, right? Because there's only one electron, how far it can travel, So it depends on number of orbits as well, but the effect of electrons is much more. And that is eventually number of electrons. If you have like, 10 electrons, or for some of the compounds, for instance, if we have like radon, we have 86 electrons. Now more of them travel to the higher energy orbits.
Okay.
That makes sense?
Yeah.
Great question. Any other questions? Okay, so that is that. And quick. So what I want to focus here is the board diagram. And since your book didn't have explicitly the image that I wanted, I just borrowed that from like this legit website, slideplayer.com. So I always advise the students to refer to scientific literatures, not Wikipedia or like random websites. But for something like this, it won't be that, complicated. But actually, this question that I always ask, that what is the total number of electrons that exist in n equal 3? And so many websites list that as 8. So what I'm saying is that even for content like this, we should be careful, because even something that is really well known, when you just Google that from internet, you can see different answers. But what I'm trying to show you here is that when you're dealing with Bohr model, I told you that I have the nucleus here, right, that has positive charge, and I have different orbits around it. N equal 1, N equal 2, and these ones, it's not accurate as I'm drawing them, because this N equal 1, actually it should be more like this. It's much closer to nucleus. And as we go as the number of n increases, it goes further and further from the nucleus. So this is like more realistic, but I kind of want to have room to demonstrate that what I'm saying, so that's why I wrote it originally like this. So I told you that the first orbit we can have maximum 2 electrons. And this is maximum number of electrons. When you have hydrogen, you only have 1 electron. So you don't feel obligated that you just should fill each orbit. It depends on how many electrons you have, okay? And n equal 2, the maximum number of electrons would be 8. So I put 1, 2, 3, 4, 5, 6, 7, 8. Okay. N equal 3, the maximum number of electrons would be 18. 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 14, 18, you know. And it doesn't exactly matter where you put it, as long as you know the maximum number of electrons would be 18. So for instance, and here you have like the energy level, this is n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, n equals c. And maximum number of electrons in each orbit. And as long as you know, for the purpose of our class now, as long as you know the first few ones, that would be enough. So if I tell you to write Bohr diagram for carbon, what you do, you go to the periodic table, read atomic number, and don't get confused with mass number. So when you read this, when you go to the periodic table, you actually see something like this. Carbon. So remember, atomic number is number of protons. It should always be a number without a decimal, right? Remember the number of students, it cannot be 12 and a half. Doesn't make any sense. So here, this is atomic number. This is number of protons, which, because your atom is neutral, that would be also your number of electrons. So if I tell you to draw the Bohr diagram, what you do, you have the nucleus here that has positive charge. And then you have n equal 1, and you're welcome to just draw till n equal 3. And as I said, technically, you know, the energy levels, you know, they become, the distance increases as we go further from the nucleus. So how many electrons should I put in n equal 1? Maximum 2. Okay, this is the maximum number of electrons in n equal 1. How many are left? I have 6 total, right? 2 of them I put in n equal 1. How many are left? 4. So you just put these 4 electrons here. And then n equal 3 doesn't have any electrons. Does that make sense? Any questions? So what if I give you, and I'm going to just write it in the same picture to save time. If I tell you to write it for neon, and neon has atomic number of 10, and I also write this number 20.18 here, so you know that this is number of protons and number of electrons, 8, which is 10. So for neon, how many electrons should I put in first shell? 2, right? And how many should I put on the second, n equal 2? 8, right? So it would be 10 minus 2 equals 8. So I say 1, 2, 3, 4, 5, 6, 7, 8. And that is the maximum number of electrons that can be in n equal 2. If I tell you to write the structure for sodium, have another color, sodium, that the atomic number is 11, you are not allowed to put another one here. The maximum number of electrons in second shell is 8. So you put this electron here. And do you remember when I was talking about different groups and elements in periodic table. I told you noble gases, they exist as themselves. They are like atomic elements. We don't have Ne2 or He2 or Ar2, and they don't form bonds with other atoms. They are all set. They don't want to participate in any reactions. And based on Bohr model, that is why. So when you have one electron here in n equals 3 in sodium, for whatever reason I delete that. Okay. This structure is not as stable as neon. So what happens, sodium likes to get rid of this electron to reach the electron configuration that I'm going to talk about in the next class. It wants to get to the electron configuration of neon. And that is why sodium loses one electron and reaches to Na+. Because just having one electron here, that electron has lots of energy. It's in n equals 3, right? I hope I convinced you that energy, when electron is n equals 3, it has more energy. It has more energy level. The energy level is higher. So this electron has higher energy, so it can move freely and easily loses that electron. Okay? But let's look at electron configuration of chlorine. So chlorine has 17 electrons. So if I want to have the Bohr diagram of chlorine, I have positive charge here, and when I try to rush, my circles become distorted. I have n equal 1, I have n equal 2, and I have n equal 3. Okay, so how many electrons I should put in n equal 1? 2, right? How many should I put in n equal 2? 8. 1, 2, 3, 4, 5, 6, 7, 8. So far I put 10, right? 2 plus 8 was 10. How many are left? 7. So I put 1, 2, 3, 4, 5, 6, 7. So what do you think if you accept from me that elements, atoms, they want to reach the electron configuration of a noble gas next to them, closest to them. So for this chlorine atom, do you think it's easier for chlorine to lose these 7 electrons here, or is it easier to gain 1 electron? To gain 1 electron is much more feasible. So that's why chlorine gains 1 electron, and we have chloride ion. We have Cl-. So that is the whole reason, and I promised you that, I told you just remember that halogens, they gain 1 electron, or like alkali metals, they lose 1 electron. I told you the pieces of our course comes together, right? I tell you why that happens, and I try to explain with number 8. So at that time it didn't make much of sense, but now it makes more sense. That is why non-metals gain electrons, and metals, they lose electrons. And depending on which group they are, it would be different number of here. So we have like some expressions that I just, have like your book picture here. So we have like excitation, and relaxation. So basically when we give, an element some amount of energy or heat, and the electron goes from lower energy level to higher energy level, we say that we have excited that electron. And let me just write the definition here. Let me see, where is it? In your book. Okay. So I just write here, based on what your book has written, when a hydrogen atom, and that can be for any atom per se. But now in Bohr model, we're talking about hydrogen because Bohr model failed for other elements. That would be the subject of next part of this chapter. But when a hydrogen atom absorbs energy, an electron is excited to a higher energy orbit. Is that clear what excitation means? Okay, great. The electron then relaxes back to a lower energy orbit, emitting a photon of light. So when we say, this electron is excited, that is what we mean. We mean that from lower energy state, for instance, from n equal 1, depending on what compound we have, right? Or, sorry, what element we have. From n equal 1, it goes to n equal 2. So from lower energy level to higher energy level. So that would be excitation. But relaxation, we have an electron that already absorbed some energy, so now it's unstable. It has higher amount of energy, and it goes back from higher energy level to lower energy level orbit. So that would be relaxation. And I give you these when I say which of the following statement is not correct. That when an electron travels from n equal 1 to n equal 3, it relaxes to its original position. So remember, if it goes from n equal 1 to n equal 3, it's being excited, right? As long as you understand what I mean here and you know where we use which expression, you should be able to answer these questions easily. And remember, when we have like the electron that is, for instance here, again from n equal 1, it traveled to n equal 3, right? It has been excited. And if from, here if your book has another example, so it would be easier to distinguish. For instance, here from n equal 4, it goes back to n equal 3. So it relaxes back to n equal 3, and in that process, it emits light. And this light would be one of the line electrons. And we talked about this. And here is kind of like explanation of what I was telling you, that depending on from which energy level this electron going back to, from higher energy level to lower energy level, depending on these energies, we have different colors. So when this distance here is higher, we have like, for instance, violet, which has like corresponds to higher energy, but this one is lower energy. So this would be longer wavelength. TH. Any questions? Okay. So I don't have attendance today because I was running out of time. So see you in next class.